on to pay attention to. You should already know this one. Now I want you to notice some things about these scales. Celsius scale starts at 0, goes to 100 as far as water is concerned. I want you to realize that that's not an accident. That's not a coincidence. In fact, the Celsius scale is actually based on water to begin with because it's a substance that we use quite often in this life. So the Swedish guy whose last name was Celsius, he decided, I'm going to make this scale to where 0 is the freezing point of water and 100 is the boiling point of water. And it's a very good idea. It's very convenient. The Celsius and Kelvin scales are actually exactly the same. And by the word scale, I mean the interval from 1 degree to the next. In other words, the amount of kinetic energy that is added to the substance from 1 degree to the next in Celsius is the exact same of kinetic energy that's added to the substance from 1 degree to the next on the Kelvin scale as well. You'll notice that the difference from 0 to 100 is 100 as well as 273 to 373. It's the same interval. But when Lord Kelvin came up with the Kelvin scale, he decided this negative temperature thing is not useful. So if we're going to base a temperature scale on water, this makes sense. Let's use the same scale so that we don't have a whole lot of confusion and fractions and things like that, like we do from Fahrenheit to Celsius, which is quite annoying. So let's not do that, but let's go ahead and base the Kelvin scale on what temperature actually is. This one is based on absolute 0. And you say, what's absolute 0? Well, absolute 0, somewhere way down here, 0 Kelvin, is the absolute coldest temperature you can get to. You cannot go any colder than that. Okay, so there are no negative numbers on the Kelvin scale. The Kelvin scale is based on absolute 0, based on the molecules of a substance. And ultimately, that one was based on water because the Celsius scale became based on water. The Fahrenheit scale is just ridiculous. There's some story about this guy named Fahrenheit, who's a German man, taking some salt mixture and trying to see how far he could cool it down, and that was his 0 point. And then he took the salt out and just put water and ice in there, and whatever it came to happened to be 32, so okay, we'll put that there. And then 100 degrees somewhere in here, he decided 100 degrees should be body temperature, and there's some other stories circulating about other things, and it's ridiculous. It's convoluted. For some strange reason, we continue to use this scale in the United States. It doesn't make any sense except for the fact that we all know it. I want you to understand the Celsius and Kelvin scale. So just so you know, some things that might be useful to you on the Celsius scale in case you go to any other countries, that's what they're going to use. Room temperature is somewhere around 22 to 25 degrees Celsius is generally considered as a comfortable room temperature. And then body temperature is actually somewhere, not 27, it's somewhere around 37 degrees Celsius. Our 98.6 Fahrenheit ends up being about 37 degrees Celsius. So those are some useful Celsius points to know. Now, back to our discussion of absolute 0. Why can there be no temperature below absolute 0? Well, if we look at, imagine a graph that looks something like this. And let's say over here on the left side is the kinetic energy of the molecules of a substance. Molecules. Right? We talked about, you wrote up here that temperature is a measure that indicates the average kinetic energy of the molecules of a substance. So let's put kinetic energy of the molecules on the y-axis and temperature on the x-axis. Temperature and kinetic energy are directly related. The higher the temperature, the higher the kinetic energy, and the relation ends up looking something roughly like this. All right? In other words, the lower the temperature, the lower the kinetic energy of the molecules. That means if I look at 3 different points along here, if I take a beaker of, again, let's just say water, here's a bunch of water molecules sitting around in here, they're going to have some random movement, some kinetic energy, and at a high temperature, they have a high kinetic energy, so they're going to be moving around quite a bit. Right? They're bumping into each other, they're moving fast, they got places to go. And the lower the temperature goes, if we look at a place somewhere in here, these water molecules, the same mass, the same everything else, but they're not going to be doing quite so good. They're not moving as fast. They don't have quite as much kinetic energy. And you can imagine what happens when we go all the way down to the absolute 0 point, 0 temperature. This is 0 Kelvin rather, we should say. 0 Kelvin means zero kinetic energy. There is a 0 point right here. It has to be. These water molecules look like this. They are rigid. They are firm. They are not moving. By the way, even if water molecules are frozen, they still move, they still vibrate, but obviously they're not going to move quite as much, and they're not free to move around the container, but they still vibrate. But you can cool this down below freezing to the point where the molecules actually set up in their rigid structure and they do not move any longer. And this brings us to the reason why there can be no temperature below absolute zero. Because, let's go ahead and write this down. Why can there be no temperature below 0 Kelvin? Because I'll say at this point there is no movement which means if you got no movement, you have no KE, no kinetic energy of molecules. There is no kinetic energy of the molecules at this point. So if temperature is the relative kinetic energy of the molecules and the kinetic energy is 0, you can't get any lower than that. In other words, you can't go slower than 0. You cannot go any lower than that. So that's the significance of this Kelvin scale, is it more accurately reflects what molecules are doing. So it's interesting to think that temperatures that we consider cold are only considered cold because our bodies have very, very high temperatures. But even the freezing point of water is 273 Kelvin. So low temperatures are actually high temperatures when we're talking about the kinetic energy of the molecules of a substance. We only start getting low when we get around 0 Kelvin, temperatures that would literally burn us because we would transfer so much energy from our bodies to that substance at one time that it would cause your cells to die. At those temperatures, you're starting to get very, very little movement of molecules, and theoretically at negative 273 Kelvin or Celsius, 0 Kelvin, the movement of the molecules ceases. You can't go any slower than that. That's the reason why absolute 0 is the lowest you can possibly go.